Hello and welcome to Neuro Navigator. Today's topic is action potential level 3. This is the last video in this mini series, but if you find yourself feeling a little lost, you can go back and visit the previous two videos for a simpler explanation. An action potential, or AP, is neuronal signaling, which is a specialized type of cellular communication that involves changes in both chemical and electrical signals. A neuron has what's called a bilayer membrane, which is represented by these little guys down here. It's created with phospholipids that create a selective barrier to ions. There are 4 ions we are concerned with for this video: potassium, or K+, sodium, or Na+, chloride, Cl-, and calcium, Ca2+. Because of this bilayer membrane, ions can only travel into the cell via channels. There are 2 types we're concerned about: leak and gated channels. Leak channels are always open, so they serve as kind of like open pores in the membrane and allow the ions to flow down their concentration gradient or down their electrical gradient. These voltage-gated channels are going to respond to voltage. However, at no point in this process will there be an equal distribution of ions in the cells. The concentrations are maintained with the electrical gradient and the chemical or concentration gradient. Both of these gradients have the ions moving to where they are either less concentrated or attracted to the opposite charge. So the electrical gradient, charge, concentration gradient is the concentration of ions. This is also why, despite the concentration of potassium inside the cell and it being a cation, the resting membrane potential of a neuron is still around negative 70 millivolts. Because the proteins inside of the cell are negatively charged, and because of the sodium-potassium pump and the calcium and chloride pumps in the plasma membrane, all the ions but potassium are pumped out. So at negative resting membrane potential, the neuron is only permeable to potassium. Where does this leave us? Well, whenever a neuron is permeable to an ion, it will move in the direction of its electrochemical equilibrium, when the concentration gradient is equal to the electrical gradient. For potassium, this occurs around negative 80 millivolts. But then, this neuron is going to send glutamate, an excitatory neurotransmitter. When glutamate attaches to an ionotropic receptor on the receiving neuron, it's going to result in a passive potential that will make the cell become slightly more positive and slightly more likely to fire its action potential. This is called an excitatory postsynaptic potential, or EPSP. Why? Because when this receptor lets in sodium, which makes the neuron more permeable to sodium, and sodium's electrochemical equilibrium is plus 60 millivolts, the ions will move to achieve that. As more glutamate attaches, as more passive potentials are created in the dendrites, and as more EPSPs make it slightly more likely for the cell to fire its action potential at the axon hillock, it could become positive enough to hit threshold, which is that dotted line up on the graph. This is where we hit a principle called all or nothing. If that threshold is crossed, it will fire an action potential. And so when that threshold is hit at the axon hillock, all of the voltage-gated sodium channels will open because of their positively charged sensors will be repelled by the positive charge. There's quite a distance from the axon hillock all the way to the axon down here. So to maintain the integrity of the depolarization, there are things along the way. These little nodules right here called myelin sheaths. So you can think of these as insulation for the neuron. In between each sheath is an area called a node of Ranvier. Each node has voltage-gated sodium channels that respond to the charge that is being passed down. More and more sodium will flood down the concentration gradient all the way to the terminal button. At the peak of this action potential, which you can see up here on the graph, these voltage-gated sodium channels are going to inactivate with this little ball and chain right here. This is called the absolute refractory phase, where sodium channels cannot open and no additional action potentials can occur. At this time, the slow voltage-gated potassium channels are going to open, responding to the same charge that the voltage-gated sodium channels responded to way back here. So now, the voltage-gated potassium channels are open. Potassium is going to move down the concentration and the electrical gradient, repolarizing the cell and even hyperpolarizing it, which is this dip right here, as the cell enters the relative refractory phase. Here, the voltage-gated sodium channels are closed rather than being inactive, and with a big enough depolarizing force, about that much, you could get another action potential to occur. But before that occurs, let's talk about what's happening in the axon terminal. Voltage-gated calcium channels are going to respond to the same depolarizing force as the voltage-gated potassium and the voltage-gated sodium channels. Calcium is going to flow in and bind to a protein called synaptotagmin. This protein is attached to a synaptic vessel. So these little lines here are those proteins. This synaptic vessel is full of neurotransmitters, and like I said earlier, that is glutamate in our example. When calcium attaches, it will bind to the plasma membrane, which is represented by this down here, fuse them, and it will release whatever neurotransmitters are inside. All right, that's it. More videos on long-term potentiation, specific neurotransmitters, and more concepts are coming soon. So follow along if you want to see those videos.